Good morning, everyone. I come from Wuhan University of Science and Technology. Now, I begin to introduce our work. Our work proposes a context and likeness-aware generative adversarial network for shadow removal. Shadow is a natural phenomenon appearing when light is partially or completely blocked. The goal of our work is to detect the shadows and remove shadows for a single input image. A high quality shadow remover image should satisfy three aspects. One, the illumination in shadow regions is effectively recovered while preserving the texture details. Two, the recovered illumination and color in shadow regions must be consistent with that of the surrounding environment. Three, there are no artifacts in the image. However, due to the complexity in shadow regions, producing high quality shadow remover images is a challenging task. Many methods have been proposed for shadow removal. Now, learning-based methods have shown their potential for shadow removal, but the existing learning-based methods focus too much on pixel-based analysis methods, which cannot effectively build spatial associations. Such methods may produce undesired shadow results, especially for shadow images with complex scenes. Look at the two examples of shadow removal. To address this problem, we propose a CL-GAN framework for image shadow removal. Our work has three contributions. We design a context-aware module which explores patch-based features and facilitates the global consistency between shadow and non-shadow regions in the shadow removal result. 2. We augment the input data of the discriminator to make the discriminator more stable and effective. 3. We use dynamic weights instead of static parameters to make the model pay more attention to shadow regions in training. This is the framework of the proposed CLA GAN. It contains a cross stage and a refinement stage. The cross stage is a UNet architecture and is used to produce a coarse shadow removal result. Images in the red box are the cross shadow removal results produced at the cross stage. The refinement stage is used to correct the cross result and predict a refined shadow removal result. Refinement stage contains a lightness branch and a refinement branch. The lightness branch is used to produce a lightness map without shadows. With the inputs of the cross result and lightness map, the refinement branch is used to produce the desired shadow remover image. Images in the red box are the lightness map predicted by the lightness branch, and the images in the blue box are the final shadow remover results produced by the refinement branch. Furthermore, we embed a context-aware module at the refinement stage. The context-aware module can make our network utilize the surrounding features as reference to character the lightness and the color in shadow regions. It makes the lightness and the color reconstruction in shadow regions more robust. The reconstructed features from context-aware module are used as supplementary information for the lightness branch and the refinement branch. The context-aware module uses the features of patches in non-shadow regions as convolutional filters to process the patches in shadow regions. Simply, we transfer features from non-shadow regions to shadow regions. The use of the context-aware module can facilitate the global appearance consistent for the whole image. Furthermore, to reduce the dependency between representations of the discriminator and the quality of the predictor results, we augment the inputs of the discriminator by rotating the corresponding image pair in different degrees. We use a loss function to provide constrained information for the network. Our loss function includes four components: coarse loss, light loss, refined loss, and the rotational adversarial loss. Coarse loss contains visual consistency loss and perceptual consistency loss between the coarse result and the corresponding ground truth. Light loss is calculated to evaluate the light difference between the predictor light map and the ground truth of the light map. The refined loss contains global loss and local loss. Especially, we use dynamic weights for local loss. The dynamic weights ensure that the model pays more attention to shadow regions gradually. Rotational adversarial loss is the adversarial loss for the network. There are some shadow removal results compared with some traditional methods. Compared with these methods, our method not only effectively recovers illumination in shadow regions, but also reconstructs the illumination and textures of shadow boundaries with less artifacts. There are some visualization results compared with learning-based methods. Due to taking context information and dynamic weights for the loss function into consideration, our CLA GAN can pay more attention to shadow regions and produce more natural and realistic shadow results. Table 1 and Table 2 summarize the comparison results on SRD and ISGD datasets. From the values, we can observe that our method presents the best results in the whole image. The best values illustrate that our results are closer to ground truth images. We use an ablation study to further evaluate and verify the effectiveness of the components in the proposed CLA GAN. We designed 6 variants to get the ablation study. The 6 variants are with or without one or two components mentioned in our method. From quantitative values in the table, we can clearly see that the CAA GAN can get the best results. This figure presents some visual results for the mentioned 6 variants, from which we can clearly see that our CAA GAN recovers the best details of the shadow remover regions and looks more realistic. The pleasant shadow remover results verify the effectiveness and the potential of the components designed in the proposed CAA GAN. There are some other shadow remover results with complex scenes using our CAA GAN. The illumination and the texture is in shadow regions are effectively recovered, and the recovered results are suitable for human vision perception. In the end, I will conclude our work. Our paper proposed a framework CAA GAN exploring contexture and lightness information for shadow removal in a cross-to-5 fashion. 1. We design a context-aware module to facilitate the global consistency between shadow and non-shadow regions. 2. We augment the input data of the discriminator to make the discriminator more stable and useful. Moreover, we apply dynamic weights instead of static parameters to make the model pay more attention to shadow regions in training. 6F want to listen. Thanks for your attention. 行了吧？